Now we're going to get into some calculus, and we're going to learn some new ideas. We're going to extend our understanding of derivatives in single variable calculus to partial derivatives in multivariable calculus. But let's start as a review. So what we have right here is it's a rod. This is a rod, and it's unevenly heated metalled rod. So different sections of the rod have different temperatures, as you can see here. So this is showing a data table of position and temperature. And what we're saying is that temperature is u of x. So it's the function u of x. The question says estimate this value, u prime of 3. So this is saying how is the temperature changing at x equals 3? Well, first of all, let's go up to this first question. How many independent variables are there? In this situation, there's only one independent variable, and that independent variable is position. It's our x value. So as we go from 3 to 4, our temperature is going up by 15. So if we wanted to estimate this derivative, we would say that we've got a change of 15 over 1. So 15 degrees per meter. That would be my estimation for the derivative. And of course, it's not completely accurate because we're looking at a point 3 and 4, and those points aren't infinitely close to one another. But this is just to get us thinking about derivatives. So if we now look at, instead of a rod, we've got a plate now. And given the x position and the y position, we can estimate some temperature. So for example, let's think about what would, I think we're still using u, but maybe it's more sense to say t as a function of x, y. So if I said, what is t of 2, 1, what that's saying is when x is 2 and y is 1, at that position, what is my temperature? And we can see going up that my temperature at that point is 135. So, so now what we're going to start thinking about is varying one of these variables, either x or y, and seeing how it affects temperature. So it says in this question, how is t varying near the point 2, 1 as we change x? So what we're going to do is we're going to only change our value x. So at this point 2, 1, we're only going to change our x value. And we're going to consider how my temperature is changing there. So in the same line of thinking, given this point, if we're only changing x at the point 2, 1, the change from 2 to 3 results in a 15-degree increase. 15? 25-degree increase. So if we increase my temperature by 1, increase my x value by 1, my temperature goes up by 25. And the way that we write this, idea of t varying as x changes only, so in other words, fixing y, we write it as t sub x of 2, 1. So this is saying the partial derivative of t sorry about that. So the partial derivative of t in the x direction at 2 comma 1. So it's, again, looking at how my temperature varies as only x varies. And the idea is we say, okay, and we did this a lot in terms of cross sections earlier on. We're going to define our new variable u of x, and u of x is looking at temperature as a function of x only, and we're doing that by fixing my y value at 1. So we're going to say let y equal 1. So all we're concerned with is changing our x value. And when we fix y at 1, when we let y equal 1, then we're just talking about a single variable derivative. And that single variable derivative is the same thing as a um, multivariable partial derivative. All right, so just defining this idea of partial derivative as looking at a multivariable system, fixing all variables except for one, and then looking at how my dependent variable changes as we change that one variable. Okay, so it says estimate the rate of change of t in the y direction at the point 2, 1. So we're talking about the partial derivative of t in the direction of y at the point 2 comma 1. So we look at the point 2 comma 1 here, and what we're going to do is we're going to fix x. So we're only looking at this yellow data set. And what we notice is that as we change y by 1, as we go from 1 to 2, my temperature is going down by 15. So my partial derivative in the y direction is negative 15 degrees per meter. So putting those two together, my Ty is cooling, the temperature is getting colder, and T sub x is getting hotter, it's heating up. All right, so to define this formally, we can go back to our limit definition of derivative, and our original limit definition of derivative in single variable calculus was saying, let's suppose we've got a point x and x plus h, and here's the corresponding y value, f of x and f of x plus h. Our limit definition of derivative said, okay, well, let's think about the slope between these 2 points. But now let's let this h value get infinitely close to 0, so that we're looking at the slope between really just one point. So exactly the same, we've got the partial derivative with respect to x here, f sub x of a and b. And what we're going to do, since we're talking about the partial derivative with respect to x, we're going to fix b. So b is not going to change. So our dependent variable, first one, is f of a plus h comma b minus f of a comma b. So notice my b values are constant. We're just changing the x by a little bit. And that's the limit definition of partial derivatives. And if we look at the next case down here, the rate of change with respect to y, what we're going to do is we're going to fix our x value now. So this is now going to be fixed. So we look at f of a, b plus h, minus f of a. So notice the a's stay the same, comma b. So we're letting our y value increase by just an infinitely small amount. So these are the two formal definitions of our partial derivatives. Now, just like in single variable calculus, in multivariable calculus, we've got a couple of different ways of notating partial derivatives. So let's say that we've got, our dependent variable z, which is a function in terms of x and y. We've got the way that we have been writing it so far, which is f sub x of xy, or f sub y of xy. Well, we can express that. The other way of expressing that is this. It's like the dz dx, but it's written like this. And what this symbol, as opposed to a straight up d, this is the exact derivative. When we write it like in this form, which is del z del x, and we pronounce this del. With that del z del x, this writing implies the partial derivative, in this case, of z with respect to x. So that's just another way of notating it. So let's think about a visual understanding of partial derivatives given a graph. So we have some function, and we can get a slight understanding of what this is. This is something like z equals negative x squared minus y squared. So it's a flipped parabola that's been lifted up along the z-axis. So some plus some positive constant, let's say like 10. It's going to be some graph. This is an equation. An equation like this would produce graphs like we see. So if we look at this first point number 1, or example number 1, what we're looking at, we want to look at the partial derivative with respect to x at this point. And so the idea is, at this point, a comma b comma f of a comma b. So remember this point x, y, z, where x is a, y is b, and z is f of a b. If we're looking at the partial derivative with respect to x there, what we've done is we fix y. So notice our y value has been fixed. So it's like drawing a it's not like, it is drawing a cross section. And the partial derivative with respect to x, we can represent in terms of a tangent line. So notice the tangent line right here. And so now interpreting what that slope is, here's my x-axis, and as I'm moving along the x-axis at this point, what's happening to my z value? Well, I'm going down. So at that point, my partial derivative with respect to x is going to be less than 0, or a negative value. And similarly, over in example number 2, where we're looking at the partial derivative with respect to y, likewise, what we're going to do is we're going to fix our x. So notice in this cross section, my x value is fixed, and the only thing that we're changing is y. And at this point AB right here, we draw a tangent line to that cross section. So we're drawing a tangent line to the cross section, and here's that tangent line. And we notice, just like before, as we increase in the y direction, so as we increase in the y direction, our z value is going down, and we see that right there. So Likewise, partial derivative with respect to y at that point is less than 0. All right, so that's a visualization of what's going on. So partial derivatives are looking at the derivative of these cross-section graphs. All right, so let's see if we can figure out whether the signs of the following are positive or negative. Now, the graphical aspect of this is going to be a little bit challenging. But if we think about Q, so we want to see if looking at Q, at point Q, is f of x positive, is f of y positive? So what I would do, to think about f of x, we're going to fix our y value. So to think about f sub x, fix our y. So we're talking about this cross section right there, and we notice that as we go in the x direction, our z value, let's get a different color, our z value is going down. So f of x is going to be less than 0. Whereas if we look at the partial derivative with respect to y, and draw this cross section, it looks like at that point, it's a little bit hard to tell, but it looks like as we go in the y direction that our point, just for a little bit, is going up. Though some might, it's hard to be convinced on these 3D graphs, but it looks like the partial derivative with respect to y is positive. Okay, so now let's look at point P. So we've got partial derivative with respect to x, partial derivative with respect to y. So if we want to look at partial derivative with respect to x, we're going to fix our y value. So we're going to get something that looks like and there it's hard to tell whether that cross section is at a max or I'm going to put hard to tell. For me, looking at the graphs, it's not always that obvious. However, when we look at the partial derivative with respect to y, so we're talking about this cross section here, there it's very clear that as we go in the y direction, that our z value is going down. So that's less than 0. All right, so that's kind of getting a visual representation and a visual understanding of partial derivatives. What about using a contour diagram? So what we're looking at is the heating in a room, the temperature in a room. And the temperature in a room is a function of distance from the heater and time since the heater has been turned on. So we can imagine that, the further away you are, the colder, and the longer it's been on, the hotter. So that's just kind of an immediate grasp of what's happening. And the question says, what are the signs of Hx of 1020 and Ht of 1020? So what are the signs? And then estimate these. So at the point 1020, we're talking about this point right here. If we look at the first one, where we just change x, so we're at a contour of 25, so 25 degrees, and if we just change x, so we're moving to the right, we go down to 20. So clearly, as x increases, our heat or temperature is decreasing. But what would be the estimate for that value? Well, it's drawn in there. So the change in temperature over the change in x, we went from 25 to 20 degrees, so a -5 change in temperature, and it took us 14 meters to do that. So to get from this contour line over to the next contour line was a change of 14. So that is our estimate for the partial derivative with respect to x at that point. Okay, very similarly, if we're just changing t, so now we fix x and we're just changing t, so we're at this point and we're going to go up, and we have to go up 32, 32 minutes, because that's our y value. So we go up 32 minutes, and when 32 minutes have passed by, so imagine the heater has been on for 32 minutes. When 32 minutes have passed, we jumped from 25 degrees to 30 degrees. So our estimation for the partial derivative with respect to time would be that there was a change in temperature over some change in time, and that change in temperature was 5, because I went from 25 to 30, over 32 minutes. So that's how you estimate partial derivatives using a contour diagram. And now what about the interpretation of the partial derivative? So just as important as being able to compute and analyze partial derivatives, so is it important to be able to understand what they mean. So let's say that here's an example. So what I'd like you to do is read this example and take a stab of it, interpreting these partial derivatives. Once you've tried to do it on your own, have a listen to my thoughts on it. Okay, so our weight is a function of how many calories we consume and how many minutes that we're exercising. So in this case, what's happening is we are consuming 2,000 calories and we exercise for 15 minutes. And what this is saying is our change in weight given a slight change in calories would equal 0.02 pounds per calorie. So in other words, at this point, when I'm consuming 2,000 calories and exercising for 15 minutes, if I continued to exercise for 15 minutes and changed how many calories I was consuming, my weight would go up by 0.02 pounds for every calorie that I took in. Likewise, over here, we've got a partial derivative of weight with respect to number of minutes. So again, I'm getting 2,000 calories and exercising for 15 minutes. And the idea is that if a change in 1 minute of exercise will result in a loss of 0.025 pounds. So there's your exercise plan. For every additional minute that you're exercising for, you lose, some very small amount, but something amount of weight. Okay, partial. All right, so now let's get to the algebraic part of it. So if we're computing derivatives algebraically, given some multivariable function right here, it says find f of x, or sorry, f sub x of 3, 2. In other words, find the partial derivative of our function with respect to x at the point 3, 2. So the steps, since we're talking about f sub x, we're going to fix y, and we're going to take the derivative, partial derivative with respect to x. And when we do this, we're treating y as a constant. So if y is a constant, we can think about this as 1 over y plus 1, because y is just a constant, times x squared. So our derivative, partial derivative, with respect to x is going to equal, well, this is just a constant, so 1 over y plus 1 times, and the derivative of x squared is 2x. And so now we evaluate that at the point given. So at the point 3, 2, that's going to equal 1 over 2 plus 1 times 2 times 3, which equals 2. So that's saying that at the point 3, 2, an increase in x of increasing x by 1 will result in our z value, or dependent variable, increasing by 2. And you'll notice that your book does it slightly differently, but follow the way that I'm doing it, because it's a little bit broader and better practice. What the book is doing is they're immediately plugging in that value of 2 into the function, but this method is a bit, while it's easier, at times it's a bit more restrictive. So do what I did. All right, so let's do a bunch of these. Follow A with me, and then pause the video and try to do B and C on your own. Okay, so if we look at A, f, the partial derivative with respect to x, well, y squared we treat as a constant, so this just equals y squared, which is a constant, times the derivative of e to the 3x, which is e to the 3x times 3. Or this is the derivative of that, using the chain rule. And the partial derivative with respect to y, now that's fixed, and we're taking the derivative of y squared, so the derivative of y squared is 2y times our constant, e to the 3x. Easy, easy, as long as you can as long as you can recognize that those when you're doing partial derivatives with respect to x, just treat y as a constant, and when you're doing a partial derivative with respect to y, treat x as a constant. So now pause the video and try the next two on your own. So for B, the partial derivative with respect to x, well, we've got something raised to the 5th, so using the chain rule, it's going to be 5 times that something raised to the 4th times the derivative of the inside, where we're treating y as a constant. So treating y as a constant, the derivative of that will just be 3y and plus 2. Done. And the partial derivative with respect to y, the first part's going to be very similar. But now when we take the inside, we're treating x as a constant. So the derivative will just be 3x. And the last one, c, so partial derivative with respect to x. We're going to need to use the product rule here. So the derivative of the first, so we've got function 1, function 2. So the derivative of the first function is e to the x plus 3y times the derivative of the inside, which is just 1, where y is a constant and x is our variable. So that's the derivative of the first times the second plus the first times the derivative of the second. And the derivative of the second is cosine of xy times the derivative of the inside, which is y. Because it's the derivative of xy, where y is a constant and x is a variable, is just y. Okay, likewise, partial derivative with respect to y. Well, the derivative of the first function is e to the x plus 3y times the derivative of the inside. Well, where y is our variable, the derivative of that is 3. Okay, times the second function plus the first times the derivative of the second. Well, the derivative of the second is cos of xy times the derivative of the inside, which is x. So now, I imagine this might be a little bit harder just because we're dealing with chain rule and product rule and partial derivatives. So take your time with these and maybe go back and review this. All right, so now we're going to look at partial derivatives when we have more than just 2 independent variables. Here we have 3 independent variables, but we treat it exactly the same. But I think what I'm going to do, which in this case is a little bit, I think, pretty helpful, we're going to say f of x, y, z equals x squared times y cubed times z to the negative 1. So just expressing that as a negative exponent. So when we find all the partial derivatives, the partial with respect to x, well, everything is a constant except for x. So this is the only thing that we're taking the derivative of. And the derivative of that is 2x. So times y cubed times z to the negative 1. And the partial with respect to y, only worry about the y. So we're going to have x squared times 3y squared. That's the derivative of this, times z to the negative 1. And the partial with respect to z, x squared is just a constant, y cubed is just a constant. And then the derivative of that, negative 1 times z to the negative 2. So it's, while it looks challenging, the algebraic steps are pretty straightforward. All right, we're going to finish this video with one more example, and then there'll be a follow-up video with a bunch of sample problems that are similar to the problems that you'll be doing. So in this problem, what we have is a vibrating guitar string, and imagine that it's originally at rest and then it gets plucked and the string starts to vibrate. And what we have here is a string that guitar string that's it's a meter long. So at its end points, the string stays fixed. But what we're looking at is the position of the string. The position of the string, so the vertical position of the string, as a function of x, which is its x position, and t, which is its time. So in other words, imagine you have your guitar here, and there's your string, and then when you pluck it, the string is going to go up, and then time passes, it's going to go up further, and then it's going to come back down, and back down, and back down. So what we want to know is, given its x position, where it is on the string, and the time, so as it goes up and down, these are all different times given the same x position. We want to know what is the height of the string. And it's given here in this equation. It's a function of x and t. So it says evaluate this partial derivative, the partial derivative with respect to x at 0.3 comma 1, and explain what it means in practical terms. Well, let's explain what it means first. What this is saying is that you're 0.3 meters from the 0 position. So in other words, if we call this 0 and this 1, we're 0.3 meters along. And 1 second has passed. If you move in the x direction, keeping time constant, so fixing time, how will the vertical height change? So to do that, we're going to take a partial derivative. So the partial derivative with respect to x, we're treating as a constant here. We're treating this component as a constant because it just has t. So our partial derivative is going to be 0.003. The derivative of sine is cosine of pi x times the derivative of that inside with respect to x, which is times pi, and then times sine of 2765 t. And then we'll plug in the givens here. So the partial derivative with respect to x is 0.003 times cosine of pi times 0.3 times pi times sine of 2765. Okay, well that's a big long thing, but if we evaluate that on our calculator, making sure that we're in radians, we're going to get 0.003 times cos of pi times 0.03, not 0.03, 0.3. Close that, times pi times sine of 2765. And this is our partial derivative with respect to x at the point 0.3 comma 1, and we get that it's 0.002. And what this implies is that changing our x position by 1 would result in a very small but positive change in our y position. And that is this. And I don't think we'll do this problem, but in this problem, what we're looking at is the partial with respect to t. So in that case, we're saying let's keep our position fixed, but let's change time and think of as time changes, will our y position go up or down at that given point position in time. All right, so this was an introduction to partial derivatives. I'm going to stop the video here, but you should plan on also watching the next video, which is just purely example problems. Thank you.